Recorder. Okay, so good morning everybody. So today is the last class for this semester, and today class is about the definition of mechatronics. Why do we have to learn about the mechatronics? The reason is in the former time, the previous head of department, Ajahn Vimont, he assigned me to also talk about mechatronics a little bit because I have experience on these mechatronic topics, and also it's also linked together to mechanics that we have learned also, so that I can share the experience and the knowledge how those two is connected a little bit before you really go into deep detail about the introduction of mechatronics in the third year. Alright, then maybe before we get into the topics, we need to know the definitions of mechatronics first. So what is about the mechatronics? So we have the core. Can I edit something here? Let me. Okay, right. So we have 4 core control system, computers, mechanical system. This is what we have learned. Okay, and we have electronic systems. Normally in the past we have only this. I would say these two is quite close together, control system and computer. So control system, we also require some programmings and also algorithms. So in the previous time we have only these 4, I would say 3 cores. We have computers, we have mechanicals, we have electronics. So we have these 3. And then in the past 5 or 10 years, we're starting to learn about the robot, and also some, for example, some controllers, new controller also. When you build a robot, do you think we can use only mechanicals, or do you think we can use only computers, or we can use only electronics? No. In real life, we have to combine those 3 main pillars into one single product, because we need mechanical to construct things that it could work in reality physically, and then we need electronics to connect those mechanical stuff into the systems. And then we also use computer science to programmings and to control those electric system that controlling again the mechanical systems. That's why in 5 or 10 years ago we also have so-called mechatronics, and I will show you how this two really bonding together, mechanical and mechatronics. Okay, so on the right side it say the mechatronics basically refer to mechanical electronic system, and normally described as synergistic combination of mechanics, electricals, electronics, computers and control, which when combined it make possible the generation of simple, more economic and reliable, okay, system. So in the later slide I also will show you how this how can I make it disappear. Alright. Oh, so that this one. Right, so And we have the system control. System and control. First, what is systems? What is control? The system is a device or process that given the input and produce some outputs. Okay? For example, DC motors. Do you know the motors? So, in the car we always have combustion engines, and it also act like a motors, but not really the same. But have you ever seen the motors? Maybe you also in the past, you know Tamiya, the car that the kids play, or it's not the kids but teenagers also play it. So we have the electrical motors, we have plus and minus sign here, we connect it to batteries. Okay, and then the battery energizes the motors, and the motors rotating. So what is the system? This one is motors, and input is voltage. Okay, and the output is rotary motions. Okay, so here is called systems. System is what you gave input and then you got it output. But it doesn't mean you have only motors here. Okay, I will show you later. It's not only at these systems. Alright, then we next page. So what about mechatronic systems? Mechatronic system, it's a little bit more complicated, but not really hard to understand. So for example, I will start with how do we start then? For example, air conditionings. Okay, we have rooms, we have air conditioning, right? So we have aircon, and this aircon also have, actually this aircon is this one, also this one, yeah. So air conditioning has actuators. What is actuators? Actuator is the device that change one type of energy to another type of energies. In this case, the air conditioning have motors also, you know. So how air conditioning works is they are compressing the air to get more pressures, and then it's also how to say, when you compress it, it also absorbing the heat energy, and then it's getting pulled outside of the rooms. Okay, so means the heat goes out and it make the room temperature going down. Okay, so we have a motor in the air conditioning to also compress the air, and also winding the air inside, winding the cooling air into the rooms. And this system we call it actuators. So actuator is just the motors that we input the electrical energies, and then it's changed into rotary energies, motions. Okay, and then in this actuator is the motors, but the plant is also include the whole of the air conditionings. And the air conditioning, they also have a sensor. Okay, so air conditioning cooling the rooms, and we have a sensor to detecting. For example, if we set the temp equal to 25 degrees Celsius, but now it's 30 degrees Celsius now, and then after 5 minutes the sensor detected that the temperature is still 28 degrees Celsius. It's going down, but it's not reached the limit. So this sensor is like an ice, or your hand, that you feel something when you touch it. It's too hot or too cold, or your eyes that you detect something. The sensor is the detection device, and in this case is thermometers, which detecting the temperature in the rooms. And then when it detecting the temperature in the rooms, they send the temperature of the room into the microprocessor or microcontroller. Microcontroller is like a brain. This one is like a hand, or for example hand, eyes, the sensoring device. And then they say, okay, it's still too hot, and then it sends signal to the brain, and the brain is processing, and then you say, oh, when it's too hot, you can just put more cooling air from the air conditionings. So here is the command signal to the actuator. Okay, brain say, hey motors, just winding more and also make the air more cooler. And then actuator make it, and then 5 minutes later, okay, it's go to 24 degrees Celsius. It's too low now. And then the sensor say, oh, now it's too cold. And then it sends signal back again to the brain. The brain say, oh, just stop the air conditionings. And then it's going into the loops, okay, until we get the set point of the temperatures. So this is called mechatronic systems. Okay. And next, so we have controllers. So controller is the device that act on the error signal. So the controller is here. Microcontroller is actually it's a brain. If we compare it to our bodies, okay, it's a brain. So it's a device that acting on the error signal generated to determine the control actions. So they get the signal from the sensor, they're processing, and then they say, okay, just make the room cooler, for example. And the evaluation performed to determine the control actions can be done by electronic signal processing. The controller requires an input of both measured indication of controller variable and representation of the reference values. So the controllers is actually require two things as an input. Of course, they need actually, if I write it, so this is a controller. Actually, controller get one signal, but this signal is coming from sensor and set parameters. This is a sensor. This joint mean, for example, this E is equal to set parameters minus sensor parameter. In previous case, I would say in the first one, we set the temperature as 25 degrees Celsius, and then we have the temperature in the room in the initial state as 30 degrees Celsius, then we get 5 degrees Celsius errors. as a negative. And then this error will signal will send it to controller, and then controller will use this value to control the electrical signal that send it to actuators. Okay. And next, for example, what is controller? Controller is actually has many types. We have, of course, computer on the left side. We have laptop, anything that have a chips that can control stuff. And we also have microcontroller or Juno. Okay. Or PICs and so on. Also, there is also a small part of small size of computer. It's like in between computer and microcontroller. We say Raspberry Pi, I think. Yeah. And then it's also possible to have a chip like this, and then you construct the controller by yourself. And you can see, for example, this electronics stuff, microcontroller and computers, it will get the signal from the sensor, and then it will process inside those chips, and then it will send back the it will send the output. For example, here is connect to the sensor. It's getting the signal here, but here they're sending the signal output to air conditioning, to motors, for example. Okay, this one E is equal to -5 degrees Celsius, but actually it's standing in form of the electrical signal. And then in here we say we will send, for example, the signal to the motor. If it's 5 degrees Celsius, we will send for example 5 volts to the motors, and then motors will running as 5 volts. And then if it's 1 degree Celsius, we send 1 volt, for example, and then motor will run slower. Okay, but it actually can be programming inside those controller and computers. Alright, then okay, next we have the sensor, and in this case the sensor is a device for measuring some aspect of the environment. This is property of the sensor. Then let's get into the sensor property first. So the sensor is conversions of the physical measurement quantity into the signal. Okay, it's change the properties, no, not change, it's measure the quantities, for example, of the temperature, speed, or displacement, or sound, or wave, or whatever. It measure the physical stuff and then change it into the signal. And then normally it's changed to electrical signal because it can be easily put into the microcontroller or computers. And then we have sensitivities. We have sensitivities here. And this sensitivity, what is this about? Okay, it is the high, if sensitivities should be as high as possible, because it will get better reactions with the respect to the quantities that shall be measured. For example, you have displacement sensor. Okay, and then it will give the signal. For example, another one has high resolutions, high sensitivity, means it can sense really good. Maybe I change the example here, might be better for the temperatures. So I have temperatures sensor, okay, and then if the sensitivity high, means, for example, if the temperature changes to 25 degrees Celsius, it will send the signal as 5 volt, for example. If it changes to 26 degrees Celsius, it changes the signal to 6 volt. So the microcontroller, when it send it, when sensor sends signal to the microcontroller can differentiate between those 2 volts, and they know that okay, 5 volt is 25 degrees Celsius and 6 volt is 26 degrees Celsius. They can differentiate between those two. But if the sensitivity is low, means 25 degrees Celsius is 5 volt and 26 degrees Celsius is 5.001 volt. So the differentiation between them is really low. You can sense not that good. But if it 100 degrees Celsius, maybe you get 6 volt. Okay, it doesn't mean it not works, but it will not work if the differentiations of the difference between those two temperatures is too low. And you can see the voltage here difference is too low to the microcontroller to differentiate the signal, and that's why the sensitivity of this sensor is low. For example, someone can sense the difference of the change of the temperature really good, but someone that has a problem with your nerve, and then you didn't feel anything, so you cannot differentiate the temperature change by 5 degrees Celsius, for example. This is called poor sensitivities. And then selectivities should be as low as possible. Why? For example, selectivities should be as low as possible because it is respected to everything else that has changed. So, for example, if you would like this temperature sensor is also has an influence from the light, from the UV light, for example, or from the sound is not good, because you would like to measure only the temperatures, but the sound or wave or whatever the other thing else that we don't want to measure is affecting to your result. For example, if you have 25 degrees Celsius, but you have a vibrations. It means the vibration is 0, so there is no vibrations happens. Then you measure the stuff as 5 volt. But if you have vibrations as 5G, this maybe you don't want to know this, but if there is a vibration from 5G, if your selectivity is not good, you will see 6 volt. But if your selectivity is good, so high select, this is low select, and high select is not good, please remember. And if it low selectivities, then means this vibration is not affecting to your results. You don't really want this, right? Because you would like to measure the temperatures, but now it's peak. The vibration have an effect to your results, so it's not good at all, for example. Okay, so stability, the constant as possible behavior with respect to all environment change like temperature or no agings. For example, your sensor today 25 degrees Celsius, today is 5 volt, but next 5 years is 6 volt, so it's not stable anymore. It's degraded or aging over time. But if you have a good stabilities, maybe you have 5.1 volt. Of course, there will be, in realities, your sensor of course will be degrading as time pass by. So that's why it's reduced the maybe it's increased or the voltage is reduced. It depends. So okay, enough for the kind of property of the sensor. And then example of the sensor we have, for example, displacement, speed, acceleration, force, torque, pressures, mass, temperatures, and so on. So actually in mechanics that we have learned so far, you can see that when we put the force, we need a sensor also, right? Then we know the force. For example, I have a problem. I say I put P as 50 newtons. How can you know it's 50 newtons? Or else you attach the sensor here and then you push 50 newtons. So actually those sensor is also really important to mechanics problem, because we also need to measure the force, we also need to measure the torque, we also need to measure the pressure to really confirm our hypothesis or our governing equation or laws. Okay, and also I have said before, you remember the Young modulus last time. How do we get it? We do the test. We have this kind of material rod here, and then we pull the force, and then we measure the displacement and then the force to find this stress strain curve, and then you get Young modulus. So how do we measure displacement? How do we measure the force? Of course, sensor. You can see that everything is connected. Okay, so you cannot really like know only the theoretical without understanding in the real world how do you get those values. So next is the sensor displacements. So this one really interesting. Before we get into this, so I also previously is about measuring the displacement over there on the left below here. So we also measure this displacement. How do we measure displacement? So I will tell you now. So you know that do you know the circuit of the electrical device? So maybe I teach you a little bit to this. So normally in electrical device we have batteries. Okay, we have, this is really simple one, we have resistance. and the battery we say is volt. Okay, and then this V equal to IR, so I equal to V over R. So this is the governing equation for this one. And yeah, so when you fix V and then you change R, then the current is changed. What does it mean, current change? So you can detecting this change by the microcontroller or the sensor. Alright, and how R change? So when you have R like this, okay, this is R, resistor, and then if you pulling the force, you remember when you pulling it, you will deform this as X, and then in Y and Z axis also reduce it also, isn't it? Yes, you remember when you're pulling on X axis and the other two axes also reduce it by ratio of Poisson ratio. So what does this means? When you're pulling it, you can see that R equal to L over A, and this L is increased. You can see it's increased by you increasing this displacement, and this area, the cross-sectional area, this is reduced, right? So when you're doing this, your R, this is a picture 1, picture 2, this your R2 and R1 equal to L1 A1. This increase from L1, so the R2 will be much more than R1 when you pulling it. Okay, and you can use this difference to detecting how much force you're putting on those valves. Okay, so but what does this related to displacement? What? So it means when you're pulling this as a displacement, for example, displacement is to change R. Okay, so it means displacement also proportional to R in some case, in other case. Mean if displacement is how to say, if the displacement is increased, means the R is also significantly increased also. If the displacement is decreased, then the R resistor is also decreased resistance, and then this R will also related to the volt, to the current, and we have microcontroller to detecting the difference of the current. Okay, then that's why we can detecting the displacement. And then to do this, please remember this strain gauge here. This is super common sensor in the world. I am for sure that you will encounter this sensor in the futures, the strain gauge. It can have many options. It can detecting the also it will detecting the displacement of this. You can see this black one. This is where we call it the S metal foil. This one acting like a resistor that I wrote before, but they're winding this like this because when you changing this displacement, the R will change a lot because when you change one displacement, it happens through every line here. Okay, the sensitivity will be much better. So if you have only one line like this, and then you have plus minus batteries, this one has really much more 5 or 1 2 1 2 3 4 5 6 7 8. It has 4 times better in sensitivities, this design. That's why they would not know, they would not do it like this, only one line. Okay, and then if you have 4 wide, but this length is really short, also the same, it's not really good sensitivity. So that's why they put the length here as much as possible that it can detecting the displacement, and also they also do it as much loop as possible, because they also didn't want this to be too big. Okay, they have to balance the sensitivities. Okay, so actually this resistive displacement measurements, this strain gauge, it can detecting the resistive or resistance change causing by the length change by the strain. This is important. And then you can see already this related to the mechanics of materials. Before, maybe you are not really understand what is this one, the strain, but now you understand, maybe. I hope you understand this. And the strain is just the deformation of the percentage of deformation of the materials. Okay, by the stress. Remember, the stress equal to Young modulus and strain. And then we have this graph, strain and stress, and then this is slope, here is Young modulus, and then here is elastic zone, no, here is plastic zone, permanent deformation, and then here is elastic zone. And then always the strain gauge will happen only this elastic zone. They don't want it to be to have the plastic deformation there. Okay, so we also have another kind of displacement sensor or angles. It's really simple. We have light sensor. This normally we use when we would like to detect the angle of the motors. So we have a light sensor, and then you can see here the black and white, and this light sensor detecting how much how the light is changing the state, because you can see when we have this white block, the light can pass through and then it go to the sensor, and the sensor detect 1. And then when this rotate a little bit, the light sensor hitting this black box, and then the light sensor will not pass through anymore, then it sees 0. And then when you rotate a little bit, you see 1 0 1 0 1 0 again and again. And this 1 0 means you have a rotations of this shaft. Okay, so this is how the optical measurements, the optical sensor of the displacement works. Okay, so the distance is divided into equidistance interval whose width determines the resolution of measurements, and the interval are counted as, and the measurement always relative to the starting point. And the speed sensors, we have many types of the speed sensors. So we can also use those this sensor, and then we stamp it with the time, and then we divide it with the time, we also get the speed. Okay, There is many type of this kind of sensor. I will show some for you. So we also have this kind of Doppler effect for acoustic waves. So this is really getting into the signal processings or the wave topics. When we sending the wave to the objects, and then when it hit the object with the if the object traveling in this velocity, when the wave hitting the objects, when it's bouncing back, it will get less frequency. You can see the width of the signal is higher than this one. The T is higher than T2, signal 2 is higher than T1. T is the period between one cycle of the signal. And then if the objects is moving toward your frequency generators, it will increase your frequency. And then with this you can use this formula to calculating your speed. We call it Doppler effect for acoustic waves. So we're using the wave properties to detecting the speed of the objects. Okay, actuators. So we have many kind of actuators. For example, we have motors. So this is not sure, maybe electrics, motors. This is I would say this is hydraulic motors. Or actuators is using the oil to moving this piston up and down. And this is pneumatics. Motors or actuators. Okay, is using the air instead of the oil or the fluid. And this is electric motors, and we have many kind of electric motors. We have AC, we have DC, and we have step motors, and we have many kind. Okay, so we'll not get into detail of this. Alright, so that's it for the first sessions, and then we will continue again.